Welcome back as we continue looking into ways that engineers gather data for problem solving. In this lesson, we're going to be talking about ideal gases. We're going to see shortly that an equation of state is an equation that relates the three primary variables that we need: pressure, volume, and temperature. You already know one of these. The one that's best known is the ideal gas law. And that says that pressure times volume equals number of moles times R, the ideal gas law constant, times T, temperature. Frequently, we're going to choose to work with specific volume, which is volume per number of moles. And in that case, the equation becomes P times specific volume equals RT. And the advantage here is that we don't have to deal with the the actual number of moles. And this, remember, our specific volume is also 1 over density. And so sometimes people will write it in this way. But I do find that this is incredibly convenient to work with and very commonly used in engineering problem solving. Now, another thing that's related to being an ideal gas, although not required that the substance is an ideal gas, but we frequently will talk about a standard state. STP is the standard temperature and pressure. Now, the standard is not uniformly standard for all applications, but for most instances, we're going to use 0 degrees C in 1 atmosphere. But whenever you see something where they say it's at a standard state, you need to look up and make sure that you really know what that means. But traditionally, the STP, standard temperature and pressure, are going to be at 0 degrees C or 273 Kelvin and 1 atmosphere. If you convert this over to degrees Rankine, that's 492 degrees Rankine. At this particular temperature and pressure for an ideal gas, the specific volume is going to be 22.415 liters per mole. Now that should be a lowercase v, not a capital V. Sorry about my poor quality typing. And if you do this for all the various states, for the kinds of moles that we typically use, whether it's the gram mole, the kilogram mole, or the pound mole, the volume associated with the standard temperature and pressure varies. And so STP gives us a relationship between standard volume and standard moles for various units. Now, frequently the way we use this is we just simply take ratios of the ideal gas law. So pressure times volume equals nRT, and we do this at the actual state and the standard state. If you divide through these, PV over PSVS equals NT over NSTS, because the R is the same in both cases. Now, of course, we can rearrange this in all sorts of ways, and one that's very convenient is that we frequently use specific volume and then we eliminate the variable n. So this is another convenient way of using this relationship. Now, the reason this is very important for engineering applications is because the most common way that people describe gas flow rates is through the SCFH or the SCMH. SCFH is standard cubic feet per hour. SCMH is standard cubic meters per hour. Now, this is deceptively looking like a volume flow rate. But this is not describing volume. It's volume if the substance happened to be at the standard temperature and pressure. But it's never at that temperature and pressure. So really what this is doing is it's describing a molar flow rate. So let's look at an example to see how this is applied. We have in this case a gas stream that's flowing at 183 degrees Fahrenheit, 1.1 atmosphere, and 40,000 SCFH. And we want to find the molar flow rate and the volumetric flow rate of this gas. Now, in this particular case, SCFH is most closely related to the mass, or the molar flow rate, Using the definitions of STP, we find that 40,000 SCFH, well, go back to the table and we see that a standard cubic foot, or a cubic foot at STP, 359.05 cubic feet is the same as 1 pound mole. So that creates for me a conversion factor. So I'm treating this as if it's a conversion factor. And so therefore, using this relationship, I find that 40,000 standard cubic feet per hour is equivalent to 111.4 pound moles per hour. So that's my molar flow rate. If I want to find the volumetric flow rate of the gas, then I need to use the fact that this is being treated as an ideal gas, and I'll use the relationship between the ideal gas law. And so, in this particular case, the actual volumetric flow rate is 40,000 standard cubic feet per hour. Suppose this would be best with dots, right? These are flow rates. The temperature over the standard temperature, these must be in absolute. Both the temperatures and the pressures. This is in 183 degrees Fahrenheit. I add to that 459.67 to turn it into degrees Rankine. The pressure is given as 1.1 atmosphere. We will assume that that is absolute. But this is indeed an assumption. Okay. Plugging those numbers in, I find that the volumetric flow rate is 47,500 cubic feet per hour. And so I have now found the volumetric flow rate. So what about gas mixtures? Well, if my mixture contains multiple gases, such as air contains oxygen and nitrogen, as well as others, it's very common that we talk about things in terms of the partial pressure. Usually use a lowercase p with a subscript to be the partial pressure of the substance in the subscript. V sub A is the volume that just A takes up in this gas mixture. The way that we use these partial volumes and partial pressures, partial pressure, P sub A, is the pressure that would be exerted by the number of moles of A that are in this mixture, if that A got to take up the entire volume. V sub A is the volume that would be occupied by the number of moles of A I really have, if it were at that pressure and I just let it take up the correct amount of volume for that pressure. So it's like if I were to segregate. So if this is my space V, and I have A and B and C, this space here would be maybe V sub A, V sub B, and V sub C, pretending that I could totally separate out the components A, B, and C. So this is partial volume. Partial pressure is if I were to make all the A's and B's and C's all wait outside of the space V and come in one at a time and measure the pressure. For a mixture of ideal gases that behave well together, and again, we'll talk more about this in future courses, but air is an example of one of these well-behaved mixtures. We call mixtures of things that act like ideal gases and act nice together an ideal gas mixture. In that particular case, then we can use an adaptation of the ideal gas law that says that the partial pressure times the volume is the number of moles of just that one substance times R times the temperature. Now the partial pressure is the mole fraction times P in this case. And so for mole fractions, partial pressure is the mole fraction times pressure. Well, if I have several different things and I know that the sum of the yi's is equal to 1, and I multiply each piece by pressure, each side of the equation, then I end up with this expression, which of course is the sum of the partial pressures equals the total pressure. So, ideal gases. This entire lesson has been about ideal gases. Do they exist? Well, no, not really. But I am going to find that there are times when it's not a bad assumption. As pressure goes to 0, as temperature gets high, this model is going to become fairly reasonable. In fact, the error is going to typically be less than 1%. 1% is not bad. Okay, for diatomic molecules, then I'm going to find that VIG for the ideal gas case is greater than 5 liters per mole. And it's going to be a little worse for other molecules. Basically, kind of a rule of thumb, I'm going to be talking about small molecules, oxygen, nitrogen, CH4, that are at near ambient conditions. Ambient being room temperature and pressure. So as long as the pressure is not much higher than what we experience on a daily basis, and the temperature is room temperature-ish or warmer, then typically I can consider small molecules to be nearly an ideal gas. For other gases, this can lead to significant errors, and we're going to be talking more about that in the next lesson.